The Mars Ascent Vehicle, or MAV, will launch from the Earth uncrewed and enter an interplanetary Earth-to-Mars trajectory for 6 months. During transit, the MAV will provide its own keep-alive power and remain in a minimum diameter stowed configuration. The MAV is designed to have a minimum mass to ease entry, descent, and landing challenges posed by the thin Martian atmosphere. Upon arrival at Mars, the MAV will begin the entry, descent, and landing phase before deployment of the vehicle on the surface. Once deployed, the MAV will stay on the Martian surface, operating autonomously for 26 months. During this time, the solar panels will be deployed to power 4 scaled-up Moxie ISRU stacks. These units will provide 9,700 kilograms of oxygen for the ascent stage by the time the astronauts have arrived. All other keep-alive functions will be powered by 2 advanced Stirling radioisotope generators that can supply power during long periods of no light. The crewed mission will arrive at Mars in early 2036 after a 6-month transit, spending 30 days on the surface to collect a 100-kilogram sample. The crew will then enter the MAV via tunnel from their rover or habitat. The MAV will then fire its first stage engines and ascend from the Martian surface, leaving behind the base with the ISRU, ASRG, and surface solar panels. Once in a circular low Mars orbit, the second stage of the MAV will separate from the first and deploy its solar panels. After phasing in low Mars orbit, the second stage will fire at periapsis to transfer into the one Sol orbit where the Earth return vehicle is for rendezvous. After rendezvous, the Earth return vehicle will leave the Martian orbit and bring the astronauts safely back to Earth.
We are Virginia Tech MAV-1, a conceptual design for a Mars Ascent Vehicle to deliver a reliable solution that minimizes mass landed on Mars while maintaining propulsive capability. Following fundamental systems engineering, the team began with defining the problem. The customer requirements laid out by RASC-AL were to deliver a crew of 2 astronauts and a 100-kilogram sample to low Mars orbit, to design a MAV that shall meet these mass constraints to ease entry, descent, and landing, and to follow these budget and timeline constraints.
To further define the trade space and ensure that our design would meet the top-level mass requirements, we utilized mass budgeting recommendations published by the Society of Allied Weight Engineers. We applied a 10% mass reserve margin and a system-wide 13% growth allowance to generate conservative limits for the vehicle landed mass and ascent mass. Our design was thus deemed to be compliant with the customer RFP if it satisfied a landed mass limit of less than 18 tons and an ascent dry mass of less than 3,920 kilograms.
Similar to the mass limit, the cost requirement was defined to derive a more conservative cost limit. A 2% inflation rate was applied to the original $2 billion annual requirement over the 10-year period. From these values, a fiscal year 2021 benchmark was determined. Based on historic cost growth, a 38% margin was applied to constrain the final allowable budget to $1.47 billion annually. The team analyzed the mission timeline to derive new timeline requirements. Ideal Earth-Mars launch opportunities only occur every 26 months due to the Mars synodic period. Taking this into account and a 6-month Earth-to-Mars transit time, the latest cargo launch within the customer's time constraints is really Q2 of 2033. Applying a 30-month buffer for system integration and test, a hard limit was set for technological development. All technology shall be TRL-9 before the year 2030. After customer requirements were defined, objectives were set to guide decision-making for the main system architecture trade. The objective is to deliver the most reliable, lightest, and cost-effective MAV design by minimizing risk, landed mass, and cost. Risk was quantified using likelihood and consequence risk matrix standards. Landed mass served as a performance metric and was measured in kilograms. Cost was measured in millions of dollars and included MAV hardware costs as well as consequential out-of-scope costs. Per the RASC-AL Q&A and NASA desired launch locations, the team prioritized the ability to launch from any latitude. As seen in the figure, the 58 potential Mars exploration sites span from the North to South Pole. Setting this requirement led the team to exclude rotational velocity gains to provide a propulsive solution capable of polar launch. Additionally, the versatility requirement was considered further in the power architecture trade.
The Delta V budget is important to the team as it defines the overall liftoff mass and size of our vehicle along with payload mass. The total budget consists of an initial ascent to low Mars orbit, followed by a one-sol injection burn. Altogether, this was determined to be 5,510 meters per second to achieve the target one-sol orbit. The team focused on liquid propulsion for versatility and ISP. A trade study was performed to compare various common propellant combinations, with heavy weighting given to characteristics such as the ISP potential using tested or flown propulsion systems, the density of the fuel and oxidizer, and storage temperatures, as a lower temperature fuel or oxidizer would require additional insulation mass. Liquid methane and liquid oxygen performed best using this analysis, followed by nitrogen tetroxide and monomethyl hydrazine.
Following the derivation of requirements through analysis of the design space, the team compared architecture alternatives using an analytical hierarchy process, or AHP. To compare the performance of architecture alternatives, the propulsion team used the rocket equation and set baseline constraints to calculate the landed mass for a given payload to orbit and propellant combination. At the highest level, there were two architectures within the MAV scope. The first mission architecture was one where the MAV reaches a one-sol orbit on its own performance merits. This architecture requires on-site resource utilization to obtain the 5.5 km per second delta V requirement while remaining below the entry, descent, and landing mass requirement. The first two alternatives can be seen using this ISRU architecture below. An architecture similar to the Apollo Lunar Excursion Module, or LEM, is shown as the third alternative, breaking the EDL mass limit at 22,500 kilograms, leading to its disqualification. The second mission architecture is one where the MAV reaches a low Mars orbit, but then requires a taxi vehicle to deliver the crew to the Earth return vehicle. This process led to 4 remaining alternatives that needed to be narrowed down on the basis of minimizing risk, mass, and cost. Before continuing with the architecture trade, an introduction to in situ resource utilization and its consequences is imperative. The benefits of ISRU could include mass savings up to 7,700 kilograms by deriving all the LOX from carbon dioxide atmospheric separation on Mars. These mass savings, without sacrificing propellant mass, enable the MAV to reach that one-sol orbit without the taxi vehicle. Some drawbacks include the added TRL risk, system complexity, and power consumption. A preliminary study was conducted as to the feasibility of a scaled-up Moxie, or Mars Oxygen ISRU experiment, for this mission. And based on a TRL of 7, the projected timeline till TRL 9 is 7 years or 2028, ahead of the 2030 technology deadline. Additionally, the R&D costs were estimated to be $221 million, which is just 1.1% of the MAV budget. Vetting this as a possibility, the ISRU was considered further in the trade. The key risks that varied across the 4 alternatives were the need for a taxi vehicle, ISRU system, the number of stages, and the need for cryogenics. Following the NASA risk management, the following scores were derived. The bottom table shows how all these risks are applied to each architecture, and the risk total is shown. Ultimately, the risk of using an ISRU is less risky than that of adding a taxi vehicle to the Mars mission. The next objective discussed was cost. A rapid cost estimation technique was applied to determine system costs for architectures. The equation and input parameters for this calculation are shown. The resulting table shows which costs correlate to which architecture. The cost of a taxi vehicle was estimated based on the cost per kilogram to Mars and the cost of the Orion service module. The need for a taxi vehicle erases these cost savings from any non-ISRU architectures. The findings from the risk, mass, and cost analyses described are summarized in the final trade where these values were weighted and normalized in an AHP. The full oxygen ISRU architecture was selected based on near minimum risk, minimum landed mass, and minimum cost. From this decision, new requirements were identified, including the need for cryogenics to prevent boil-off, additional power for the ISRU, and a required liquid oxygen production rate of at least 0.52 kilograms per hour for the planned surface stay. Once the full oxygen ISRU architecture was selected, the team began to optimize the design. The final design consisted of a 2-stage ascent vehicle, solar panel power system, and a minimum volume crew capsule. We will now dive into our subsystem design.
Next, we will discuss the MAV propulsion systems. After analyzing the propellant consideration study, liquid methane and liquid oxygen was selected for the first stage, as this combination allowed the team to take advantage of the landed mass savings an ISRU system can provide. Nitrogen tetroxide and monomethyl hydrazine was chosen for the second stage, as the delta V requirement is relatively low, a pump-fed ISP is not necessary, and there is a high reliability of hypergolic pressure-fed engines that may be used for this application. First stage engine count was determined by analyzing thrust ranges for individual engines with the assumption of a single engine out capability aboard the first stage to minimize risk. It was determined that 3 engines with a thrust range of 90 to 110 kilonewtons each could provide propulsion for the first stage to reach low Mars orbit in a nominal flight scenario. Various engines were then compared with respect to ISP, mass, and thrust. Using this analysis, the pump-fed Avio M10 engine was selected, as it provides the necessary performance in a low mass package. For the second stage, engine out was not prioritized here, as there is a significant heritage and reliability of pressure-fed hypergolic propulsion systems in space. A single pressure-fed engine with a thrust range of 20 to 30 kilonewtons was selected to provide thrust to reach 1 Sol from low Mars orbit. After comparing several engines of interest, the AJ10-190 engine was selected, as it provides the necessary performance and has a heritage of reliability in space systems.
The attitude control system used by the MAV consists of 16 bipropellant R4D11 thrusters. Fuel is supplied to these engines through the pressure-fed NTO-MMH propellant that is shared with the second stage engines to reduce mass, bringing the total system mass to 190 kilograms. The R4D11 has been used for in-orbit maneuvering in the past on the Apollo missions, the Space Shuttle, and now on the Orion capsule with 100% system reliability.
Spherical propellant tanks were chosen to minimize the stresses and consequently the mass, and aluminum lithium alloy 2195 was chosen due to its low density and high strength at cryogenic temperatures.
The storage of fuel and oxidizer is a mission-critical field. The similarity in boiling points of methane and oxygen allow for the cryocooler system to be the same for each tank. The cryocoolers are part of the 90K cooler class, which is the industry standard. When estimating cooler mass and power, a zero boil-off system was used for estimation. To reduce mission risk, redundant coolers and electronics will be implemented, along with the addition of heat interceptors. The estimated cryocoolers are capable of maintaining the tanks at 90 Kelvin with a zero boil-off over the time from departure of Earth till ascent from Mars. When scaling up the ISRU to produce 9,700 kilograms of oxygen, the Mars Oxygen ISRU experiment, Moxie, which is currently on the Perseverance rover, was analyzed. The system takes in the Martian atmosphere, which is then compressed. This is then heated in a solid oxide electrolytic cell. The oxygen is then liquefied and put into the tank while the separated Martian atmosphere is vented out. When scaling up the unit for use, the solid oxide electrolytic cell and the compressor decrease in mass and consume power as a result of the scaling up of production rate. The electronics, structure, and thermal components are scaled by the change in surface area. These scaling factors were used to optimize for the ideal stack configuration, from which it was determined 3 stacks that produce 1 kilogram per hour each would allow for the scaled up Moxie unit to produce enough oxygen. Each stack is a 30% margin, and an extra stack is brought for redundancy purposes.
Next, we will move on to our power subsystem. One of the largest trades for our mission design was in regard to our power generation architecture. We used STK to find the time that MAV would be in sunlight at each latitude to constrain our solar panel cases and determine the mass of the ISRU units. The landed mass and power required were then found for each architecture. The solar panel and RTG hybrid power generation architecture were chosen due to its low landed mass of only 11,700 kilograms, while meeting the versatility requirement that enabled the MAV to operate at any latitude. Additionally, the use of solar panels minimized risk and complexity due to the ultraflex solar array's 100% past mission success. During transit, all solar panels will be in a stowed configuration, and the only systems that will need to receive power are the avionics and cryogenics, which are referred to as the MAV's keep alive functions. These keep alive functions, which require 3.6 kilowatts of power, will be met with the two advanced Stirling radioisotope generators. Additionally, the transit vehicle configuration has a maximum height of 7.1 meters and a width of 6.2 meters, which enable it to be stored in the 8.4 meter short payload fairing on the SLS Block 1, as well as capabilities to accommodate larger SLS payload fairings as well as the SpaceX's Starship. Once the MAV is delivered to the Martian surface, the 4 surface-stay ultraflex solar arrays are deployed using a motor. The ASRGs continue to power the MAV's keep alive functions, while the solar arrays power the ISRU units and the oxygen liquefiers. A trade study was conducted on different ASRG fuels, and curium-244 was chosen due to its high energy density, abundance, and shorter half-life compared to other possible fuels. The ultraflex solar arrays are also equipped with solar tracking using a gimbal, as well as shadow elimination by raising and lowering the solar panels to get out of shadows cast by the MAV and other solar panels. The ISRU and ASRG base is the interface between the vehicle's legs and the Ascent vehicle. It contains 4 ISRU stacks, 2 curium-244 ASRGs, as well as a radiator and vent system that acts as the thermal control during both transit and surface stay. This structure also provides support that attaches solar panel lever arms to individual motors and provide clearance between the thrusters and Martian surface. Additionally, the inside of the base contains 2 air intake vents for the ISRU units. This is to reduce the amount of Martian dust that would get inside the ISRUs by raising the intakes above ground 2 meters and shielding them from the Martian wind.
During the ascent phase, batteries will power the MAV from launch till it circularizes in low Mars orbit. Once in orbit, the solar panels are deployed and they provide power to the MAV. Power estimations for the second phase came from scaling down pertinent International Space Station systems such as mechanics, command and data handling, guidance, navigation and control, and other key systems. The in-space power generation configuration is comprised of 2 deployable panels, each with a radius of 2.46 meters, which are covered during the surface stay. The panels during the launch will have 2.6 and 1.1 Gs of load applied to each of them during the first and second stages of the launch, which is well within the manufactured limit of 3 Gs. 16 RCS thrusters located on the MAV will conduct short burns for rendezvous and docking purposes.
The structure subteam designed the structural components of the MAV. The crew capsule must accommodate 2 astronauts. To determine an appropriate size for the capsule, historical data for habitable volume of a capsule versus the crew number was collected and is shown in the graph. The habitable volume was estimated to be 4 cubic meters for a crew of 2. The total volume was determined by using the lunar module as an analog, resulting in a goal of 6.5 cubic meters for the design. The resulting dimensions of the capsule are shown in the figure.
The capsule structure is made of sandwich paneling, which consists of aluminum honeycomb core and aluminum skins, and the thrust structure is constructed out of aluminum 2024 due to its high yield strength. FEA was used to design both structures to exceed a safety factor of 1.25 per NASA standard 5001B.
The human and payload subteam ensures the safe transfer of the crew and the 100-kilogram sample. The astronauts will wear IVA suits during ascent to reduce depressurization risk and will sit in recumbent seats. The seats can be folded when not in use and provide sleeping accommodations. Anthropometric data was used to size the seats, which ensure they fit inside the crew capsule and can accommodate any astronaut up to a 95th percentile male for height and weight. After ascent, the cabin will take over providing life support. The capsule was designed to provide life support for 2 days, as the mission will be a maximum of 44 hours. All NASA human flight standards were closely followed to ensure the safety of the astronauts. The cabin has a mixed atmosphere to reduce flammability with consumable CO2 scrubbers. Due to the short mission timeline, most life support can be consumable, such as the food, water, and waste management systems.
Upon completion of the mission, the crew will enter a Martian rover with a pressurized environment similar to the MAV, where they will change out of their EVA suits and into IVA suits. A tunnel will then be connected to the hatch of the MAV, allowing the crew to enter. Once the one sol orbit is reached, the MAV will dock with the ERV using the NASA docking system. The NDS is an androgynous system which allows for connections to be made with a matching part about any single axis of rotation. Once firmly docked, the NDS has an 813mm wide tunnel, which will be opened, allowing for the transport of both crew and payload into the ERV. During flight, the 100 kilograms of Martian soil will be stored in an Apollo-style lunar sample return container.
The MAV will not require additional radiation protection for the crew, as there are 3 non-structural options which reduce exposure dramatically, which are outlined in a parametric assessment of lunar and Mars Ascent Vehicle synergy. Not using the MAV as a long-term habitat, the 44-hour total crewed mission duration, and time of solar particle events with the Mars eclipse will limit radiation exposure. The TCS is loosely based on Orion's TCS due to the similarities in mission requirements and environmental heat exposure shown in the tables to the right. The TCS consists of an active system which collects thermal loads from the MAV. 4 full-length and 2 split radiators reject heat through 2 independent coolant loops, which run simultaneously for safety. A pump circulates hydrofluoro ether, the coolant, and cold plates cool the equipment. The passive systems are the thermistors and wire heaters, and multiple-layer insulation thermal blankets for thrusters and engine nozzle thermal protection. Now let's talk about the comms. The chosen communication system is based off the Mars Perseverance rover because of its proven functionality in successful missions and its hardware redundancy. The MAV shall utilize 3 antennas. A UHF antenna will communicate with the current and future communication satellites orbiting Mars. X-band high and low gain antennas will talk primarily with the Deep Space Network, but all current orbiters are equipped to receive and transmit X-band as well. The UHF and LGA are omnidirectional, however the HGA is directional by nature and therefore needs to be on a gimbal to point at its target. Orion's avionics system was used as the basis of MAV's avionics system due to the similarity in mission requirements and scope. The Honeywell Vehicle Management Computer is responsible for the command and data handling of the entire system. This system is internally redundant via independent computational checking and TT Ethernet network interface controllers, which process data 1,000 times faster than the ISS and the Space Shuttle. The MAV will have prolonged exposure to radiation while on the surface due to Mars' thin atmosphere, and will have exposure in transit. Therefore, all electronics must be radiation hardened for high levels of exposure over a 7-year lifespan to account for 2 Mars mission windows and stored in a protected environment when possible.
Here we have the final vehicle mass tallies. As a reminder, we were targeting an overall mass reserve margin of 10%, and we were compliant with customer requirements for a landed mass of less than 18,000 kilograms and an ascent dry mass of less than 3,920 kilograms. On the left, our landed mass budget shows an itemized breakdown for each system, the mass growth allowance applied for the individual components, and a tally of the total mass. The proposed design had a predicted landed wet mass of 11,700 kilograms. This was below the derived 18-ton limit to be compliant. Furthermore, this proposed design had provided a mass reserve margin of 41.5%. On the right, the same data is presented for the ascent mass budget. The proposed design had an ascent wet mass of 18,300 kilograms and an ascent dry mass of 3,580 kilograms. Again, the dry mass is below the derived limit to be compliant and provided a higher mass margin at 28.4%. Therefore, the design was found to satisfy all top-level mass requirements.
The table on the left shows the cost broken down by system with applied growth allowances. The costs associated with the MAV total to $11.9 billion after all cost growth allowance has been applied, including an additional MAV test unit. This resulted in a 41% cost reserve when compared to the $20 billion budget, falling in the 30 to 50% range, indicating a good margin for a PDR level design. The table on the right shows cost by year to demonstrate theme compliance. When compared to the earlier derived cost limit of $1.47 billion annually, shown as the yellow line, the annual spending in blue remains below for each year. Consequently, the aggregated total spending remains under the total cost limit. With these margins, surplus funds could be directed to accelerate research and development costs to mitigate the possibility of schedule delays. This risk management visual details the largest risks considered in the MAV-1 mission. The matrix maps the risks in the table to the appropriate likelihood and severity. Crew-related risks were considered more seriously by using a logarithmic likelihood scale. Arrows indicate the risk's position after mitigation. The greatest crew risk is unavoidable due to rendezvous and docking, though the statistic of 1.1% is assumed to have improved from 2008 to the 2036 crew launch date. The greatest project risk is the possibility of ISRU TRL delays, which is mitigated by a 2-year margin between the expected 2028 TRL-9 achievement and the 2030 technological development deadline. The greatest mission risk is ISRU production failure, mitigated by bringing a redundant Moxie stack equaling a 33% margin. The timeline below shows the MAV from the development period to the flight period. The development timeline highlights the development of key technologies ahead of the 2030 technology deadline, including both the ISRU and ASRG. Simultaneous manufacturing, test, and integration from 2028 to 2030 prove the busiest and most expensive years, though the associated annual budget remains compliant with the 38% cost margin. The flight period shows the timing for the cargo and crew mission and how the ISRU leverages the 26-month synodic period for propellant production without increasing mission duration. In conclusion, the MAV-1 has a landed mass of 11,700 kilograms, or 41% EDL mass reserve. The MAV-1 budget is $11.9 billion, or 41% cost reserve. The MAV-1 is capable of reaching one Sol without the need for a taxi vehicle, greatly reducing out-of-scope costs and mission complexity. The MAV is versatile in its ability to launch from any location on Mars due to the coupled power system proposed in this design. Finally, the success of the MAV will ensure the development and heritage to enable future ISRU-dependent space missions as we continue to explore the final frontier. We would like to thank NASA RASC-AL for making this competition possible, as well as our now alma mater, Virginia Tech. A special thanks to our faculty advisor, Dr. Kevin Shimpall, and everyone who has supported us along the journey. We appreciate you.